So I started out my career as a philosopher, and I'm still an affiliate in the philosophy department at Berkeley, as well as a psychologist. And you might wonder, what do philosophy and babies actually have to do with one another? Why would I have called my book The Philosophical Baby? And for many, many, many years, philosophers, you could read essentially 2,000 years of philosophy and not actually know that babies and children existed. You could conclude that people reproduced by asexual cloning. Why would it be that studying babies and young children might tell you something about really big, deep philosophical questions? And that's just briefly what I'm going to talk about today. So here's one of the big, important, mysterious questions that philosophers could have been asking for all of those years. And that big question is, why is it that we have children at all? I mean, not the immediate reason, which we all know about, but from an evolutionary perspective, why is it that we have children? Human beings have a much longer childhood than any other animal, and yet that seems sort of paradoxical. I mean, basically, babies are useless, and arguably worse than useless, because we have to put so much time and energy into taking care of them. Why would we have this long, extended period of immaturity? Well, in fact, if you look across many, many, many different species of animals, you see a very interesting correlation. And the correlation is that the longer the childhood, sorry, let's do this the right way. There we go. That correlation is that the longer the childhood, the bigger the brain and the smarter the animal. And actually, the poster animals for this correlation are not even mammals, but birds. So if you look across different kinds of species of birds, here, for instance, on this side, you can see this is actually a New Caledonian crow. And New Caledonian crows in particular, but crows and corvids and ravens and so forth in general, are incredibly intelligent animals. So this is actually a New Caledonian crow on the cover of Science, who's learned how to use these, turn these little pieces of wire into hooks to get food. And in many respects, we've actually been doing some studies with these crows. In many respects, they're smarter even than primates. On the other side is our friend the domestic chicken, and domestic chickens and turkeys and ducks and geese and all the rest, with apologies to any chicken lovers in the audience, are basically dumb as stumps. So they're very, very good at pecking grain. They're not very much good at doing anything else. And the explanation for, so in general, you see this correlation between these kinds of animals, sometimes called altricial birds, with relatively large brains, highly intelligent, and then these precocial birds. And what you find out is that whereas the chicken is mature within a couple of weeks, the crows are immature, are fledglings, for as long as a year, which is a very long time in the life of a bird. And these New Caledonian crows are actually fledglings for as long as 2 years, which is an extremely long time in the life of a bird. And we seem to see this kind of correlation between long childhood, large brain, smart, flexible animals throughout the animal kingdom. We, of course, are all the way off on the end of the distribution. We have the largest relative cortices, at least, the thinking parts of the brain. We have the most flexibility and intelligence, and we have by far the longest period of maturity. My son is 23, and at least until 23, we're still writing checks for tuition. All right, why would we see this correlation? Well, the explanation, at least one explanation, is that using our kind of strategy, the intelligence strategy, the strategy of learning a lot, is a very good strategy for existing in lots of different environments. But it has a big drawback, which is that until you actually do the learning, you're going to be helpless. So you don't want to have the mastodon charging at you and be saying, what shall I do about this mastodon? Maybe a slingshot? I could try inventing a bow and arrow now. You want to have actually done all that learning before you actually have to face the harsh realities of the world. And the way that evolution seems to have solved that problem is by giving us a long early period, an initial period, in which all we have to do is learn and explore and find out about the many different environments that we live in, and then a later period where we can take the things that we've learned about and actually put them to use to do all of the practical things that we need to do. So one way of thinking about it is that babies and young children are really the research and development division of the human species, and we grown-ups are production and marketing. So they're the blue sky guys who just get to think about lots of different possibilities, and we're the ones who actually have to take those ideas that we had when we were little and put them to use to actually continue to survive and thrive. You can actually see this kind of picture even when you look at babies from a neurological perspective. So this is a famous slide that shows the number of brain connections that we have at various stages of development. And Piero set this up for me very nicely before. What you can see is that actually the time when we have the most connections is before we're 5 years old. And these are 3 different charts that show different parts of the brain, so that, for example, in the visual cortex, where our visual system works, by the time we're about 1, we've actually made all the connections that we're going to make. And what happens in each of these areas is we have an early period where we're make lots and lots of new connections. There's lots of new things going on. And then later on, there's this period when the connections that have been used a lot are kept and maintained, and ones that aren't used actually are pruned and disappear. So we actually have less brain, in one sense, as we get older than we do when we're younger. And that represents, that could describe a difference between this early period when there's all of this learning and exploring and plasticity going on, and a later period when we're actually starting to tune up all the things that we developed when we were younger. And one of the interesting things to notice here is that this part of the brain, the prefrontal cortex, is sort of the executive office of the brain. It's the part of the brain that's responsible for things like long-term planning, inhibiting impulses. It enables us to do many of the things that we can do. And that part of the brain is actually the latest to develop. And the most recent studies show that probably by 23, it's sort of starting to kick in, but it continues to develop all the way through adolescence. Now, that's typically seen as being problematic, and you'll often hear people complaining about the fact that babies and children don't have a frontal cortex. But if you think about this kind of division of labor, where you have an early period where you're really designed to be doing a lot of learning and exploring, and then a later period where you're starting to learn how to act, it might be that not being able to do quite as much inhibition and planning is a good thing from the perspective of a creature that's designed to learn, and I can talk about some more of that later on. All right, if this picture is right, we might also expect that from a computational perspective, and again, Piero kind of set this up, we might expect that these baby brains would be designed with very powerful mechanisms that would enable them to do a great deal of learning. And again, that's exactly what we've discovered. And in work that my colleagues and I have been doing, we've shown that babies are using a lot of the same kinds of techniques, statistical techniques, techniques for understanding the world that were described by this man, Reverend Thomas Bayes, and are the basis for a great deal of what's going on now in statistics and machine learning. So if you want to know what's going on inside of this baby's head, we think it actually looks something like this. This is a page from Reverend Bayes' notebooks. These babies are unconsciously making very sophisticated kinds of calculations about how the world works. And they're unconsciously working in much the same way that scientists did. Really what Reverend Bayes said is that the way that you learn is by making hypotheses about the world around you, probabilistic hypotheses, looking at evidence and updating those hypotheses on the basis of the evidence that you get. And we have more and more evidence that that's really what's going on with children. My first book was called The Scientist in the Crib, and there's a paper that we just did in Science a couple of months ago reviewing this really extensive evidence showing the way that babies are using the same kinds of processes as scientists. Well, what is it? How could we possibly say this about little babies, about 3 or 4-year-olds? If you asked them, are you using conditional probabilities to update your subjective credences, they probably wouldn't give you a very intelligent answer. So the way that we ask them, and the reason why there's been such progress in our understanding of babies and young children, is by asking children questions in their language instead of our language. And their language is the language of real action on real things in the real world. So what we do is give children this little device. This is what we call the Blicket detector. It's a machine that lights up and plays music when you put some things on it and not others. And it turns out that we can use this machine to show just how much the children know. So here's an example of one of the experiments we've done in my lab. What the babies do is they see a red block. And the red block, we start out by simply asking the kids, how could you make this machine go? And the children all think that the best way to make the machine go is to actually make contact between a block and the machine. They don't think it's very sensible to just wave the block over top of the machine. But then we give them this pattern of data. We show them that 2 out of 3 times waving the block works, and putting the block on only works 2 out of 6 times. And then we simply ask the children to make the machine go. And what we find is that 4-year-olds will consistently choose to wave the red block over the machine rather than to make contact with the blue block. So they've overturned that original hypothesis based on this probabilistic data. And remember, these are 4-year-olds who are just starting to add and subtract. Nevertheless, they seem to be able to do the math and figure out that there's a higher probability of activating the machine this way than that. And notice also that actually the proportion of the red and blue matches the probability of the red block versus the blue block. And we've done other experiments that shows that that's actually consistent. So these very young children, these 4-year-olds, are already doing a statistical analysis of the data and using it to change and update their hypotheses in just the ways that Reverend Bayes would have said. Another way that we scientists solve problems is by doing experiments. And it turns out that children do experiments too, but when they do experiments, we call it getting into everything. And a whole lot of experiments, a lot of our kind of experiments in the last 5 years or so have started to show that just children's everyday play and exploration is really a kind of experimental research program. And let me just show you one clip from the lab of Christine Laguerre of a little boy who's trying to figure out how the Blicket detector works. And what he's seen before is that yellow ones make it go and red ones don't. And now he's seen an anomaly. One of the yellow ones doesn't work, and the experimenter says, why did that happen? And this is what happens.
This one's lighting up, and this one's not. So that means making this light up.
Now, if you had any doubt about whether they were like scientists, every scientist in the room at least will recognize that miserable expression. I don't know, he says.
Oh, it's because this needs to be like this, and this needs to be like that. That's why.
What should we do now?
Oh, because the light goes only to here, not here. Oh, the bottom of this box has electricity in here, but this doesn't have electricity. It's lighting up. So you need to put 4. So you need to put 4 on this one to make it light up, and 2 on this one to make it light up.
Okay, so that little boy is incredibly adorable and cute, but it turns out that he's actually quite typical of the 4-year-olds that we and Christine and others have tested. So when we look at 4-year-olds, what we see is in their everyday they're really exploring a range of hypotheses. And not only are they exploring and testing those hypotheses, but they're testing a much wider range of hypotheses than, say, the undergraduates that we test at Berkeley test. And we can actually show that systematically in experiments. And you can see that just in that little clip, that that child is, over the course of those few minutes, trying all sorts of weird, unlikely possibilities that we wouldn't have thought of. Well, what's it like to be one of these creatures? What's it like to have one of these brains that's making all of these connections, doing all this high-level Bayesian computation and exploration? Well, if you ask people traditionally about consciousness, many philosophers and so forth have thought that babies and young children were less conscious than adults. They don't have some of the adult abilities to do things like use language. I think what it's like is actually to be more conscious than adults. And there's actually a few experiments that suggest that this is true. For adults, one of the things we know about adults is we know that adults are very conscious of the things that they pay a lot of attention to. But we also know that for adults, that attention has a very, very narrow window. People sometimes describe attention in adults as being like a kind of spotlight. So we're very conscious of just the things we pay attention to, and then we are very unconscious of all the other things that are going on around us. We even know something about the brain physiology of this. So what happens when you pay attention to something is that something called acetylcholine, certain kinds of neurotransmitters, are squirted onto a little part of the brain. And the rest of the brain has inhibitory chemicals, chemicals that actually shut down all the other parts of the brain. So that feeling you have that one little part of your world is very vivid and everything else has gone dark actually fits the neurophysiology of the brain. And we can show this by doing things like looking at eye movements. So here's an experiment that Scott Johnson and Ed Voll did, where they just tracked the eye movements of adults and babies sorry, let me go back for a minute. If you look at babies, you see something very different. So babies and young children are very bad at, we say they're very bad at paying attention. What we really mean is they're very bad at not paying attention. So they're very bad at actually just focusing on one thing at a time because they're so busy seeing everything else that's going on in the scene. And when we look at their brains, we see the same thing. Those babies' brains are just bathed in these cholinergic transmitters. They're extremely plastic. They don't just change in the places where they're paying attention. They change whenever there's something new or interesting or unexpected that happens. And we can show this, and this is from an experiment in which they recorded the eye movements of babies and adults as they looked at the same scene. This is a scene of Charlie Brown and Snoopy. And what you can see is what happens with the adults is the adults start out looking at Charlie Brown and Snoopy's face, and then the film unfolds, and they basically, their eyes just stay on those two objects all the way through the film. When you show the same film to one-year-old babies, here's what happens. So the babies start out looking much more widely. It's not that they're just random. Once it starts, they start paying attention to things, but they're paying attention to the stars and the edges and the snow and many, many more different kinds of aspects of the scene. So if you think about the adult's attention as being a spotlight like this, where we just pick out one thing at a time, the baby's attention is sort of more like this. The baby's attention and consciousness is more like a lantern that's actually illuminating everything that's going on around it. So our kind of moral is that consciousness is actually narrowing, that we're going from this infant lantern to this adult spotlight. So again, what's it like to have this kind of consciousness? Well, I think we can get a taste of it as adults when we put ourselves in the position that babies are in a situation in which we're taking in lots of new information at once, and we can't rely on the kinds of things that we already know. So traveling is a really good example of that. When we go to a new place, what happens is not that our consciousness goes away, becomes attenuated. On the contrary, we can spend, I can spend months in Berkeley essentially being a zombie, driving and going to faculty meetings and teaching. And for faculty meetings, it's probably a good idea to be a zombie. And then I go to the conference in Paris, and for those 3 days, I'm actually really alive and awake and paying attention to what's going on around me. We also know, this is somewhat bad news, that those cholinergic transmitters, those plasticity-inducing transmitters that I talked about, are what's in nicotine. So when people smoke, cigarettes actually do make you more vividly conscious of what's going on around you. They kill you, but in the meantime, you actually can pay better attention. And caffeine has the effect of getting rid of those inhibitory chemicals. Remember, I mentioned for adults, we have inhibitory chemicals that actually shut down lots of our brain. And one of the things that caffeine seems to do is to lift some of that inhibition from our brains. So if you want to know what it's actually like to be a baby, here's what it's like to be a baby. It's like being in Paris in love for the first time after you've had 3 double espressos and a pack of Gauloise cigarettes. This is a beautiful André Bresson photograph from the 1920s. And that's a fantastic way to be, but it does mean that you tend to wake up crying at 3 o'clock in the morning. So I'll stop there and see if people have questions.